In this problem, we need to rank these molecules in order of, say, decreasing stability, or you can say increasing the heat of hydrogenation. So to do that, we're going to be analyzing whether we have conjugated and isolated system and also the degree of substitution of the double bonds. So let's see what happens in molecule A. In molecule A, we have this is isolated double bond. Notice that here there's no conjugation. This is an sp3 carbon. There's also sp3, so no conjugation. So we're going to label this as isolated double bond. That is also isolated here, and that is also isolated. In the other molecules, let's see, do the same analysis. Here, the double bond, this right here, that is an sp3 carbon, and that is also an sp3 carbon. That means that this double bond is isolated. However, here I see that the double bonds are double, single, double. This is a conjugated system. So one conjugated system and one isolated double bond. The other thing that is important to notice in this series is that all molecules have the same number of carbon atoms and of hydrogen atoms, so same molecular formula, but now the bonds are double bonds in different places, right? So different connectivity. These are constitutional isomers. This molecule are constitutional. Just reviewing concepts, say. So now we're clear that isolated here have one isolated, one conjugated system. We're going to do the same for the other two molecules. Here, this double bond, notice this carbon I'm pointing at is sp3. That's also sp3, and what that means is that this double bond is isolated. And I see here in the upper part that here you have conjugation, so double, single, double. So I'm going to highlight the conjugated system. That's conjugated. So it looks like they're similar in energy. So one isolated double bond and a conjugated system. Going to molecule D, I see that this is extended conjugation. Double, single, double, single, double. So all electrons are delocalized all over here. So fully conjugated. Right there, that says that this is the most stable molecule. So ranking from most stable to least, I'm going to say that D is the most stable. So most stable. And then here in this two, in B and C, I have one isolated double bond and a conjugated system. Looks like very similar. So I'm going to go here and I see three isolated double bonds, so that's the least stable. So I'm going to put it at the end. I'm going to say A is the least stable. So stability is decreasing that way. So now, how do I decide which of these two molecules, B and C, is more stable? Let's look at the degree of substitution of the double bond. So now, in the double bond above, if I look, this carbon has one hydrogen and one substituent. In this also, one hydrogen and one substituent. So this is a di-substituted double bond. In looking at here, I am comparing B and C. That's also one substituent here, one substituent here. That's also di. So this applies to the two here. So that doesn't help me, so I need to see what happens with the conjugated system here. So let's find the degree of substitution. This double bond right here, two substituents, one here, so this is tri-substituted. And then looking at this here, this carbon, one, two substituent, this carbon, one, two substituent, so that double bond is tetra-substituted. Now looking at the, on the right-hand side, here, one substituent, and here one substituent. So it's actually di-substituted. And looking at this carbon, I have 1, 2, and then here I have 1, so that is tri. And we learned that in alkenes, in a series, a homologous series with the same number of carbons and hydrogens, the more substituted the alkene, the more stable it is. So that's the case, we have the same number of carbon and hydrogens. So we have here tri and tetra substituted versus di and tri, so B is more stable. So the most is D followed by B, and then C, and the least stable is that. In terms of heat of hydrogenation, that reaction, that's less heat of hydrogenation. The reaction is exothermic, but this will evolve less heat, there's more heat of hydrogenation. And so, and stability is decreasing from D to A.